Hi everyone, and welcome back to the Towards Data Science podcast for an episode I've wanted to record for quite some time now. So there's this idea in machine learning that most of the progress we see in AI doesn't come from fancy algorithms or new neural architectures. Instead, some say AI's progress has been driven by scaling up compute power, data sets, and model sizes, and besides those three ingredients, nothing else really matters. Through that lens, the history of AI really becomes the history of processing power and compute budgets. And if that turns out to be true, then we might actually be able to do a decent job of predicting AI progress by studying trends in compute power and their impact on AI development. And that's why I wanted to talk to Jaime Sevilla, an independent researcher and affiliate researcher at the University of Cambridge's Center for the Study of Existential Risk, where he works on technological forecasting and understanding trends in AI in particular. Now, his work's been cited in a lot of cool places, including Our World in Data, which used his team's data to publish a whole expose on AI progress. And Jaime joined me to talk about his work, his predictions about the future of AI, and all kinds of other cool stuff like that on this episode of the Towards Data Science podcast. I'm really excited about this particular episode. I've been following your work generally on trends in compute and the reasoning behind all your work as well, like for quite a little bit of time now. And I'm sort of one of these lurker fans of yours. I think it's fair to say, like on Twitter and other platforms. I'm really excited to share this story with hopefully the wider world, or a larger part of the world. I'd like to start with your motivation, like getting into the space. Why trends in compute? What is so important about looking at trends in compute at this stage in our life as a species, let's say?
One thing that I am really interested in is the advent of advanced artificial intelligence. There's like some reasons to believe that in the coming few decades we're gonna see like drastic advances in the practice of artificial intelligence, which is gonna allow us to automate more and more of society. It's gonna have like wide-ranging implications from like many new jobs being created, other jobs being destroyed, but also changing the way we approach society and introducing like new risks into the mix that might radically alter society forever. One thing that I was really interested in looking into is trends in like inputs into like machine learning systems. Like people have been quite focused in like measuring outputs. We have like really good benchmarks in order to assess like how well are we doing in tasks in computer vision, how well are we doing in tasks in language models. But in the coming years, we have come to learn that there is like lots of gains that can be had just by taking like the systems that we already have and just scaling them up, just making them bigger, making them have more parameters, training them for longer, and like using more data in order to train them. And while there has been like some work exploring like these implications, there really hasn't been like a historical survey of like exactly how many resources have we been putting into like these systems. And this question is critical because it's gonna allow us to understand like all this progress that we have seen in the last 2 decades, which amount of that is due to us having like a smarter architectures, better ways of like approaching the problem of artificial intelligence versus us just having like better computers and more data to train these machine learning systems on.
Yeah, and that makes perfect sense. It kind of gives us a window into the future. It's the only, as far as I can tell, it's one of the very few, at least, ways we have of projecting what the future of AI might look like. We don't really know how to go from like an architecture or a concept of a model to what its capabilities are likely to be. We tend to be surprised when we find new capabilities emerging. So it's kind of, yeah, it is helpful to have like at least investment in the amount of dollars or the amount of compute invested in these models as a hard number, so we can say, okay, this much money or this many GPUs gets us this kind of model, and then what can we expect from the next? A lot of your work, though, is focused specifically on this idea of transformative artificial intelligence. And this term, TAI for short, it means a lot of different things to different people, and it's a source of great debate within the community. I'd like to start with that then. So like, what is transformative AI, or what is TAI to you? And how do you think about it in the context of your work and research?
Right. So for me, essentially, the way that I think about TAI is that TAI is gonna be to us as like the industrial revolution was like the farmers that precede us. Like it's gonna be something that's gonna enable like a new feedback loop in our culture, which is drastically gonna speed up the economy. And like I'm leaving this kind of vague because it's kind of like okay, we know that this is going to be a big deal. Like we know that like being able to automate like a large part of our working society, like it really it really like changes things. It allows you to it allows tasks to be done like at unprecedented speed if you don't need like a human in the loop to that is like kind of like bottleneck in the whole process. And more than that, is like, okay, well, it doesn't make sense. Like, I don't spend too much time thinking about exactly what it means.
One reason I've heard for not worrying too much about that, and I'd be curious to get your take on this, but essentially, once you get to the point where we have genuinely transformative AI, where we have something like an industrial revolution, but powered by AI, progress is going to be happening so quickly that whatever set of criteria you use to define this new industrial revolution, if you slightly disagree with someone about those criteria, you're going to be off by like a week, or you're going to be off by like a year, let's say, and then the next level of the criterion is going to be reached. And so there isn't really that much fuzziness at the margins because change is going to happen so quickly anyway. Is that a fair characterization?
I think that is a fair characterization. I think that for most plausible definitions, that makes sense of like how society might be transformed. Like we are gonna find them to be like extremely correlated. They're gonna happen at the same time, as you say.
Okay, no, that's helpful, and I think for people who are less familiar with like forecasting, especially forecasting AI stuff, hopefully that adds some context. Great. So essentially, we have this idea of massively transformative AI that transforms the economy, and as you said, I mean, going beyond that is really hard also because I wouldn't expect like a an agrarian society, a member of an agrarian society, to be able to predict what iPads would do, what Zoom would do, and so on. So we're going to be in the same position relative to our future selves in that respect, at least. I am curious. So, like, what are the stages that have led us to where we are today? Then in the story of the evolution of AI that may eventually lead to transformative AI. So, like, you've studied that story and you're trying to use it to predict when this moment of TAI or this phase of TAI will happen. What are those phases? And like, can you give us a bit of a taxonomy of like the history of AI up to today?
So in terms of like the what we have seen so far, what I've been doing with my colleagues is like collecting information about like historically important machine learning systems since the 50s up until today, right? And then like when you look at the inputs that have gone into these systems, like so far we have looked into the amount of parameters that like each of these systems had, and like the amount of compute that was used to train the systems, like the amount how long they were trained for, in a sense. And what we have found is that in terms of parameters, it was like actually like fairly less clear the whole story. There's definitely like this upward trend, which is undeniable. But it seemed to be like fairly uniform up until maybe like 2016, 2017, 2018, like somewhere around that era. Like something happened, and the something that happened is that language models started scaling like way faster in terms of parameters than anything else that was going on at the time. This was like our first clue of like, okay, there might be like some things, there might be like some changes that are happening in like the history of machine learning that is changing the returns to scales of those systems. Like it's making it so that scaling up those systems faster than there is an incentive to scale those systems faster because we're getting like better and better performance continuously. We looked then at like trends in like compute, in like for how long the system was trained for, like how many operations in the computer it took to train the system. And then like we see like a much neater picture. We already knew from some previous work that there had been like this phase transition somewhere around 2010. So essentially before that, the trend in like the compute used to train machine learning systems, essentially it was doubling every 20 months. Uh, if you're familiar with like Moore's law, so like Moore's law is like this empirical description of like how the computing power of like our laptops or computing devices has scaled over time. which also follows like a similar pattern. Like every 20 months, roughly, you can say that things got computation got like twice as cheap, right? So what we were seeing before 2010 is that, like it's not that people were investing more into machine learning. It's more like our laptops were getting better and better. Like researchers were using like a state-of-the-art laptop for all of these things. So they were naturally coming to use like more and more resources of computation. But something changed around 2010, which is that suddenly like this trend like speeds up. Before it was doubling every 20 months. And then like afterwards, we argue that it started speeding up to doubling every 6 months or so. And this is like very fast. This is like two doublings per year, which is like fairly crazy if you stopped to think about it. And there might have been like a few reasons for this. The most salient story is that around 2010 was like the time where like we realized the potential for like deep learning systems to like perform really well in tasks, primarily in computer vision.
Yeah.
So
no, sorry, go ahead.
yeah, so it served kind of like as a wake up call for like researchers all over the world, being like, okay, there was like this paradigm that really was developed in the past century about like creating like this neural architectures that were just shown like a bunch of examples, and through back propagation they were like adjusted in order to get good performance, and that really hadn't gotten anywhere. Like we had like lots of like bespoke systems that were being developed these days, like SIFT, which like were what you used if you wanted to have good performance in computer vision. And now suddenly you have like this very general approach, which works on like a wide array of tasks, particularly at the time in computer vision, which like now we suddenly really can use because our computers have gotten like good enough to do it. And people started investing like way more into like these systems, which meant that this trend of like, okay, before the computing power that was put into machine learning systems was just the computer power you have at hand. Now people actually had a budget to like train their machine learning systems, and that budget got scaled up and up as time went on, which meant this rapid increase in like the amount of compute that was being poured into like this state-of-the-art machine learning systems.
Okay, so if I understand correctly, at this point we have two distinct eras that you've flagged, or actually maybe three. So we have first this phase where we have a steady, a flat academic budget, and thanks to Moore's law, compute's getting, yeah, as you say, twice as cheap every 2 years or so, and so you see, twice as much compute being used every 2 years. But it's still only academically interesting during this period. There's no real industry application to the tech, or at least the industry applications aren't enough to get people to throw tons of money at it. And then around 2010, we have this moment where there's an inflection point in compute budgets. And would you say that was due to AlexNet specifically, or were there other things? Because I remember when we talk about the history of deep learning, AlexNet is often cited as this like big aha moment. Everybody goes, oh, the deep learning revolution, it started with AlexNet. Is that genuinely true, or are there models that came before that sort of hinted at, oh, you know what, we should scale more with the compute? Or like, what's your sense of that, of AlexNet's role in that story?
Right. So in my book, what characterizes the era of like deep learning is like three basic factors. One of them is about the model size and depth. Like suddenly we started getting like systems that had like multiple hidden layers in like their architecture, and like had like way more parameters than what we had seen before. The second one is the use of GPUs. So people started experimenting with like GPU platforms in order to parallelize the training, which like drastically increased the amount of like computing resources that they had access to. And the last one is like performance. That was the point where like, yes, suddenly deep learning systems are starting to top the charts of in benchmarks like CFAR, like the image recognition benchmark CFAR, or and other tasks. Now, was AlexNet the first thing that did all of those things? And the answer is like definitely not. We have seen like very large systems, like as large as like AlexNet since the early 2000s. Like there's a paper by Viola and Jones in 2001, where like they train a system which is essentially as big as AlexNet. It's GPU-based training, the thing that distinguishes AlexNet. And it's like, well, also not, because we have been seeing like the use of like this insight of like using GPUs to train machine learning models had been around for like at least 7 years by then. Like for example, in 2005, there's this paper by Steinkraus and other people where like they show some machine learning systems that were trained on like GPUs. And in fact, I can remember right now exactly when like the CUDA GPU framework was released. That was definitely like a watershed moment in which like suddenly like GPU computing became like very ubiquitous and like really easy to program also for machine learning applications. All right. So it's not. AlexNet is not special in terms of model size. It's not special in terms of like GPU-based training. Is it special in terms of performance? And it's like, yes, it significantly outperforms like prior techniques in ImageNet. Now, it was not the first benchmark that had been broken by a deep learning system. Like the other example that predates it is there is this paper by San and others in 2010, which makes substantial improvements over the previous state on the art on MNIST. And there is like also this paper by Mikolov, where like they also break like an important NLP task, the Wall Street Journal task. So AlexNet, it was as big as things that came before. It had been trained on GPUs, but also things that came before. Like sure, it broke like a really important benchmark, but there were other important benchmarks that were broken. Like 2 years before, around 2010. All of these factors combined kind of like made me think that okay, this is not AlexNet was not like a watershed moment out of itself. It was part of like a larger trend. But what it's undeniable is that AlexNet gathered like a lot of like academic recognition and also outside of academy. And I think it's quite plausible that it acted as like this wake up call where like people were like, oh shit, this works.
Okay, interesting. So that was what I was going to ask next was like, given that that seems to be the case with AlexNet, why is AlexNet held up as this ultimate exemplar of like this great watershed moment? So your assessment would be something like it has to do with people's reaction to it. Perhaps in some sense the marketing around it was just really good. Do you think that's too reductive, or is that like roughly accurate?
I think that's basically correct. It's undeniable that ImageNet was like a very important benchmark, and it was more important than the benchmarks that were broken before. But like in a sense, this gives me hopes, right? Because I kind of have to like you could have predicted AlexNet. This is what I'm getting at. Like
Right.
if you were in 2010 and you were squinting your eyes really hard, you will have seen like all these neural network papers that were breaking like this Wall Street Journal task, this MNIST task, and you will be like, hey, something is happening here.
Interesting. Okay, so that's actually, it's especially interesting given the next phase in the evolution of machine learning, because I would make a similar mistake. So in 2020, OpenAI came out with GPT-3. I can describe it to you the way I would naively have described it before this conversation, as the first pseudo general purpose AI, the first AI that was trained for one narrow task like autocomplete and turns out to be capable of a very wide range. I mean, obviously we see transfer learning in other contexts, in images, for example, but this is really where we see zero-shot learning in all its glory for the first time. Translation, coding even, essay writing, basic web design, all those things that this one system can do despite being trained to do something really qualitatively different. So my guess is you're going to come back to me with the same similar story as AlexNet. Hey, you could have seen GPT-3 coming. I'd love to explore that. First off, if you agree with that, maybe you won't. But like, could you have seen GPT-3 coming? And if so, like, what were the warning shots? What were the things that should have had us going like, oh, okay, scaling does make sense?
Right. So here there is like this very interesting story, right? Like we have seen this transition between like pre-deep learning era to like the deep learning era. Now, what I want to talk about is what the next transition that we argue exists in our paper, which is the transition between like the deep learning era to like the large scale area, to the point where like industries started investing like millions of dollars into like training these very large machine learning systems in the hopes of like getting like increased performance. And when we were looking at the parameters, like it became obvious to us that okay, there's like around 2017, 2016, something around there, like parameter language models started getting like much bigger. And immediately the thing that came to us is like, okay, this is Transformers, right? Like Transformers came out in like 2017. They quickly proved to be on like a different regime of scaling, and it became like much more advantageous to like scale them up as fast as possible, and that's what happened. Um, Now I am not so sure about that, because when we look at compute, sure, we see that language models like have stolen the thunder this last years, but really like the first system we'd see that came close to that regime of scaling is some reinforcement learning systems that were spearheaded by DeepMind. So things like AlphaGo, by DeepMind and Google generally. Like AlphaGo is like one example. The Google neural translation machine is another example. Like for me, this is the point where like companies realized that they could like scale things up like 100 times bigger than they had been done before, and like actually get good results out of that. So they just went and did that. Could we have from this predicted GPT-3? I was just still like I was personally like really shocked about like the whole GPT-3 thing and like the whole rise of like language models. I was like quite bullish on thinking that language modeling was like what I will call like an AI complete problem. It was like a problem so hard that like we were gonna get like general intelligence before we actually got like good language modeling. And like, well, reality has proven me like very wrong.
Yeah, that in itself is an interesting aspect of all this. The link between scale, the link between architecture, and then the actual capabilities that are achieved by these models. What's easy, what's hard. It seems like, I mean, this is to me one of the interesting aspects of your work. It allows us to start to notice when our intuitions were just completely wrong. Now, one thing I do want to touch on before we go more into that direction, because I think there's a lot to talk about when it comes to kind of capabilities and linking those to scale and other things. It seems like you mentioned a couple times, your assessment of doubling times for compute power, for example, and your thinking and your analysis, and you're hinting in that there might be disagreement, there might be other perspectives too, which I guess to me I always found interesting because I would have expected this to be a very naively like straightforward thing to calculate. We have a bunch of leading models and they have a certain amount of compute power consumption, and then we start to draw straight lines on log plots, and there's our doubling time. So can you explain? Like I'm sure I'm wrong, by the way, but I'd love to understand how I'm wrong.
Absolutely. So let me talk about the work that came before us in terms of like compute trends. The main piece is this article by OpenAI around 2018, where like they went through the same processes as us on like a smaller scale. They like gathered the amount of compute that was used to train like around like 12 to 18 state-of-the-art machine learning systems throughout the years, and they plotted it, and they were like, okay, this is the line. Let's just run a regression, and they got like a doubling time that was like way faster than us. It's still, like our doubling time was also really fast, like 6 months. Their doubling time that they found is like half of that. It's like every 3 months things were like doubling, right? And then what happened? Well, 2 years went by, and like their prediction was, well, that their implied prediction, right? Like this implied trend, like it stops flat. Like it just doesn't go on. It's like we suddenly we hadn't seen like a doubling since 2018 by 2020. And there's in fact like this blog post by Alex Lisov where like he expands on like the work of like AI and compute, adding like a few points and being like the trend stopped right when you wrote the blog post.
Right. Now this is, are you referring here to the scaling laws for neural language models paper? I think that was 2019 though, wasn't it?
No. This is a
Oh,
blog
AI and
post that they
compute.
wrote.
Sorry,
Yeah,
yeah.
AI and compute.
Okay.
That's right.
I then want to bring in that scaling laws for neural language models paper, which came out in 2019. I think by the time they wrote it, GPT-3 pretty much would have been built internally in retrospect, because I think they released the paper for GPT-3 sometime in January, and I think the scaling laws paper might have come out in like very late 2019. So maybe they had some new insights based on GPT-3, but do you have a view on on that paper? Did it cause you to change your perspective? Is it consistent with your analysis or?
Absolutely. So the paper on like scaling laws is essentially like the whole motivation for like this whole project. It's kind of like the proof of concept that like scaling matters and is like really important. So kind of like what we see is like our work is like complementary to what's happening in the scaling laws paper. In there, like they were running like a series of experiments with some systems. What we're doing is like we're looking at what has happened historically and like see like given the insights that we found in like that paper and like some other papers that we're studying returns to scaling, whether we can explain how much of the progress we have seen in the last 2 decades is based on just this is scaling, things getting bigger and faster, versus us having like better architectures. The trend that OpenAI had found when like they look and they plotted like this line of like up to it was doubling like every 3 months, and then like Alex like continues that, and then it just doesn't grow. And like like between the biggest system in like 2018, which is AlphaGo, one of the versions of AlphaGo 0, and the biggest system in like by 2020, which is like GPT-3, is like actually GPT-3 is smaller than AlphaGo 0. So it seemed like, oh, the trend has stopped, but like really, I think that this is like an illusion that is being caused by like this discontinuity that we had in 2016, like this point where like suddenly companies started investing like 100 times more. So then what's going on is that if you just look at the biggest systems overall, you're gonna catch like a lot of noise, and that's gonna make it so that the trends that are apparently there like really are not there because they just consist of like these few outliers and include like these large discontinuities. So you need to like take a bigger look to look for like the trends that are there. And like even having like that bigger look, you still are gonna have points like in 2016 where like suddenly things skyrocket up by like 2 orders of magnitude, and that's something that happens. Discontinuities happen.
What this makes me wonder is where these trends would start to break down, or like what might cause these trends to break down in the future.
So these trends right now are the combination of like two factors. One is compute getting cheaper, as building like better infrastructure for computing. The second is investing going up, right? Investment going up. Like industries, primarily industry at this point is more and more interested into having putting like millions and millions of dollars into training these systems. Uh, these two trends like follow different mechanics and may break down because of different reasons. For the compute trend, this is like Moore's law. People have been claiming that Moore's law is gonna die like very soon. Eventually, it has to die. Like it cannot go on forever. But it's like really hard to find out what is the point at which like actually the things break down. Like we stop being able to like scale up our systems. Like there might come like new ways of conceptualizing like computation that might allow us to like keep squeezing like this trend, like keep our it's kind of like a sort of like self-fulfilling prophecy where like people kind of have like this like my impression is that internally like hardware companies have like this impression of like this is the goal to meet, and they put like a lot of effort into like making it. At some point, like physics says stop, you cannot go on. But for the time being, it hasn't sound like has slowed down a bit, but it's still happening. It's still decreasing exponentially the price of compute, and I will expect to decrease exponentially at the very least for the last 10 years, and like possibly for and like quite possibly for longer, even for how long it has held up so far. Now, the second trend is about investment. Like investment is more complicated because, well, industries have a budget and they can siphon like part of their R&D budget towards AI. And like that's essentially what has been happening. They also have like larger revenues that they can put into this. But there comes a point where like, when AI is like 90% of your research budget, you just
Yeah.
cannot go on without like a state support or like something else. When are we going to reach that point? So my colleague Tamay Vasiroglu actually performed an analysis based on a blog post by Ryan Carey from a couple of years ago, and he essentially tried to put like an estimate on like what is going to be the reversion point, where it's going to be the point where like this trend of like increased investment is going to stop, and like the driving force between progress from now on is just going to be like Moore's law. And essentially like he was estimating like under some reasonable assumptions about like how much money could companies like possibly spend on AI R&D. Like maybe in like it seems definitely plausible that it's gonna held up for like 10 years, the current trend. And then like afterwards it's like extremely uncertain like what's going to happen, if they're gonna like hit the ceiling and just stop increasing their budgets, if like state actors are gonna like come in and like keep investment up. uh we know.
One interesting factor in that analysis too is like if companies start to scale up their compute budgets in that way, eventually you do get systems like GPT-3 that can create so much value themselves that it pays for that compute, and so you have this positive feedback loop that has no termination point, or at least no clear termination point. Arguably, we're already seeing that with GPT-3. There are companies that have raised tens of millions of dollars that are really just like a fancy wrapper on top of GPT-3 or maybe AI 21 Labs products or stuff like that. And so, it's like $10 million. Well, that's already the cost of making GPT-3. So we're in a way, we're already in that regime, or maybe we're not. I mean, do you think that we may be already at this point where we're kind of closing that loop?
I think we are. Like one of my leading hypotheses to explain like this discontinuity that we saw around 2016 is essentially, yeah, the point where like industries did the calculation, be like, okay, we can afford to put this money in because this is going to generate like so much revenue. And for me, like the leading example of this is not GPT-3, it's like DNMT. Like DNMT, the Google Neural Machine Translation System was like one of the early examples of like a really, really large scale machine learning system that broke with the previous trend and that had like huge economic implications.
Okay, yeah, no, that makes perfect sense. And actually, okay, so now we've talked about this idea of trends in compute. One of the things we haven't talked about is how we tell when a particular level of compute leads to a particular capability or a particular situation in society. This TAI threshold, transformative AI threshold that you've been trying to kind of project and predict. And one of the techniques that you've used to actually land that plane and figure out, okay, how do we get capabilities from these systems? How do we predict capabilities from scale? Is to lean on this framework of biological anchors in predicting transformative AI. So could you explain what biological anchors are and how they relate to some of your work?
Very badly, but I will try my best. So essentially, within my group, we have been focusing on like inputs, but some people on this area that have in high regard have been figuring out like what to do with like the estimates that we're providing, or have come up with like their own models where like extrapolating these trends to try to forecast different levels of performance. And definitely so far, like the most intricate piece of research and the most complete piece of research that we have seen is Ayakota's draft report on AI timelines, where like she comes up with like some generally useful concepts in order to try to understand how much compute will be needed to train transformative machine learning systems. So that's the this by that's that there's like this anchors report where like comes up with like 6 different ways of estimating like what's gonna be like the amount of operations that you're gonna need in order to train these transformative systems. And like three of them are like essentially like biologically based. There's like estimations about like the so far the only example of like artificial general intelligence that we have is humans,
Right.
right? And like what well, not artificial but general intelligence that we have. And so it provides us kind of like with like a very crude estimate of like an upper bound on like how many operations you need in order to create intelligence. And there is like multiple ways that you can go about thinking, like how many operations do it take to make a human. Like one thing that you can do is just go like, okay, like a human like is born, and then like it takes like some time for it to like absorb like the culture, to like learn how to speak, how to write, how to code, how to do different things. And like it's gonna take them like, okay, roughly like 20 years to become like a functioning adult, from like a baby that knows nothing to like a general intelligence that can perform like a wide array of like economic tasks. So you can like sort of estimate like, okay, how many operations does it take in your brain to do all that learning? And that's gonna be like a sort of like estimate of like how much it takes from like baby level artificial intelligence to like human level artificial intelligence. Um, as this, there's like a couple other ways that you can go about it, because you can say like, okay, but babies have already like a lot of like built-in machinery, and like maybe this is not the best way of thinking about it. And maybe you can go with like the most extreme estimate that C provides is like going like, okay, how much did it take? How many operations did it take to like evolve a human?
Right.
How many operations? If you see the Earth as like this giant computer that has been running like this evolutionary algorithm for like billions of years, like how long did it take to actually create human level intelligence from that? And she also provides that kind of estimate. And those are the biological anchors, right? Uh, for me, actually, the ones that are more interesting are not the biological anchors themselves, but the anchors are based on like this concept of like horizon length. So essentially, what AI proposes is that systems where like the reward is like farther away temporally than the action are gonna be like harder to train. That systems where like the reward and the action is like closely paired together, and which makes a lot of sense.
Mm-hmm.
The one of the hardest problems in like machine learning is the attribution problem, like trying to attribute like, okay, this reward I'm getting, like to which action is it due?
And I guess this also, I mean, it aligns to some degree with the evolutionary anchors perspective, just in the intuitive sense that when you look at like animals we tend to think of as stupid, they tend to act on instinct. In other words, they tend to respond to immediate stimuli and respond to it in an immediate way. There's very little plotting and scheming going on in the brain of an ant, for example. Whereas when you look at dogs, maybe they can learn to train their owners in certain ways, or trick them into doing certain things. So there's a little bit of foresight and planning. Monkeys more so, and maybe humans even more so. So I guess there's a sense in which they are sort of aligned, even if they take different directions.
Exactly, that's it. So essentially, what I did was coming up with like an estimate of like, okay, so far we have trained like some reinforcement learning systems that are able to act in like these time horizons, are able to act like so many steps into the future, and then like C comes up with like an estimate of like, okay, how many steps will it take to like create a company, for example? Like this is an
Right.
example of a task, right? And then she goes like, well, this is like a time horizon of like a year. The amount of steps that this is going to involve is like such and such. And then like given that, like from the previous data on like how much compute did it take to train like these previous machine learning systems, we kind of have like a rough estimate of like how many operations does it take to train a system that has like a certain horizon length. So now with like these new horizon lengths for this task that we haven't automated yet, this could be like a plausible estimate of like how many operations will it take to automate those as well.
So through that lens, I guess this makes me think of the GPT-3 context window, or the context window of language models, as being this very important number, the sort of amount of text it can keep in mind at the same time as it predicts the next thing. Is that like, do you think that's a correct way to think about it? Like the context window might have a lot to do with this idea of planning ahead and time horizons?
Absolutely. I think this is one of the main reasons why right now, like I don't see GPT-3 as like something that can scale up to general intelligence, because you do really need to be able to like create loops in your intelligence to be able to like pay attention to things that happened like a very long time ago in order to like create that. Now, this is not to say that GPT-3 cannot be like a critical component of like artificial general intelligence. Like I have been actually like very shocked by like some kind of like by hybrid approaches in which like GPT-3 has kind of been put into like a loop in which like it is able to produce things like mathematical proofs, like code, and like that code is executed. And we could see maybe like like this as the beginning of like maybe some sort of like loop system in which like you ask GPT-3 to provide like a piece of code, the code is executed, that provides like and that provides context for like the next call to like GPT-3 GPTX like interface.
Interesting. So, and that actually vibes, I guess, with the idea that we have GPT-3 taking up, and historically AI has done this too, even going back to like the mid 2000s. It almost starts with like taking away some of the most menial tasks. So like Excel spreadsheets remove things that require like thinking on the order of a couple of seconds. I don't want to have to multiply all these cells together. Excel will do it for me. Then the next step is like, I want this to do, calculate my p-value, so do even more sophisticated operations that save me more time. And gradually the human gets to zoom out more and more, think more and more, well, we say often think more strategically, but really think over longer time horizons as the goal or the responsibilities of this AI start to expand. And so when we look at some of those loops, I guess you probably have, when we talk about theorem proving with something like GPT-3 or Gopher or things like that, I guess you probably have the human doing almost strictly long-term thinking, and then the AI picking up the slack. Is that how you're seeing those loops?
Maybe I definitely think like in the next 5 years, what we're gonna see is GPTX systems like language models and like different machine learning systems as kind of like an augmenter of like human intelligence, where like there's gonna be a human in control, which is gonna be prompting the machine learning system in order to like produce text, to produce code that then like the human is going to bet and decide what to pick. I actually wrote the abstract for my paper using GPT-3, part of it. And I expect this is going to become like a way more common occurrence in the future. I see this as different from like what I was saying before. What I was saying before, like don't take it with a grain of salt, because this is like me who's like a relative outsider to like the nitty gritty of like actually training the systems, like trying to think about like how you could scale GPTX systems to like general intelligence, and being like not very convinced about that.
Well, so this is actually interesting because there's a lot of debate in the forecasting community, as I'm sure you know, between people who are like who adopt this inside view perspective, who say, look, the best way to predict trends in AI capabilities is to talk to the people who are actually building these systems, as you say, doing the nitty gritty work. And then people will say, no, actually, the outside view is usually better because when you're on the inside, you kind of can't see the forest for the trees. And I've seen this in startups, right? Where like it's a classic thing in Silicon Valley. You have investors who have like built, let's say, an ed tech startup. And because they've built an ed tech startup, they know all the ways that ed tech startups can fail. They know all of the horrible list of things that need to go perfectly right in order to make this work. And so they'll never invest in an ed tech product because they just see all the reasons it can't work. But then they see a product in a completely other domain that they know almost nothing about, and they get really excited about it, and often they make really good bets as a result. So paradoxically, your experience can actually detract from your ability to make good predictions. I wonder how you see that interaction, acknowledging obviously we all have our biases, we all come from one perspective or another. As you mentioned, if you're more on the outside doing less building, maybe that'll default you to that side. But how do you think about that trade-off in the context of your work?
Absolutely. So when I think about predicting trends predicting like what's going to happen with artificial intelligence, as with new technologies in general, like I say there's like there's two things here. There's like trends and there's continuities. And like trends are often like surprisingly robust. Like there's this work by Impacts where like they try to set up to try to look for discontinuities so they could understand better in which conditions do this technological discontinuities happen. And like among like all the examples that they looked at of technological trends, like actually they didn't find that they found like, okay, I'm gonna say they find like a lot of discontinuities, like around like 30% of like the trends that they looked at, they found like a discontinuity, but they were explicitly looking for discontinuities. So this kind of like implies that like discontinuities are like somewhat rarer that like one might naively think, and you can actually get like pretty far ahead, which is like plotting like a straight line on like what you have seen so far. Now, if you want to go the next level, then you need to account for the possibility that there's going to be discontinuities, like the one that we saw in like 2016 with like compute and capabilities of machine learning systems. And for those, like the best you can do is like having like having like an inside view system, like trying to understand what are like the driving forces behind like the different trends that you see, and like try to understand like how incentives might change in such a way that this continues happen, or like how some certain like critical points might be reached where like suddenly things go faster. One interesting insight is that it's quite like we should naively expect like these continuities to surprise us on the positive side, because if a discontinuity happens on the negative side, like kind of like that's gonna be rolled over by the trend, right? Like
Right.
the trend is still gonna go on unless like whatever are the forces like driving the trends like subside. But normally that's gonna be like something more gradual and predictable. If you really want to, if you really want to, so kind of like as I see my work is providing like an upper bound on like how far away intelligence can be, and then like I don't have that much to say, being like, okay, like I'm somewhat confident that by the end of the century, like we will have the resources to train like artificial general intelligence. As an example, like don't take this figure literally,
Yeah.
but then I'm not gonna have that much to say, being like, okay, it might come like 40 years earlier. We don't know. Something unexpected might happen.
And actually, that ties into something we started with, which was this question of transformative artificial intelligence. And we talked about that definition. And then you just raised in this context artificial general intelligence. And when we were talking about biological anchors, it sounded like we were talking about artificial general intelligence as well, just because we were focused on what would it take to replicate the human brain rather than what would it take to transform society. I'm wondering, like, do you think that there's a functional or important difference between predicting TAI versus predicting AGI, predicting transformative AI versus predicting general intelligence? Or are they going to roughly come at the same time and it basically won't matter?
Right. Like I think there's like an important difference in the sense of like I think there's like some scenarios in which like we get TAI where like we don't get like strictly speaking AGI, in the sense of like being able to do like everything that a human brain can do. Like you don't need to be able to do everything that a human brain can do in order to like radically transform society.
Right.
Uh, yeah, I think we should focus on like predicting like the minimal the automation of like the minimal amount of transformative tasks with like actually change society. Like that's a smaller subset of like artificial general intelligence, but I also like fully expect that like in most scenarios like these two things come like fairly attached to one another.
I guess it's like for the same reason that regardless of what your definition of TAI is, you're going to get it roughly right because progress will be happening so fast once you hit it that, like, for the same reason, TAI and AGI kind of become pretty close just because progress is happening so fast. And unless there's a fundamental reason that we can't get to AGI, as you say, like unless our algorithms just can't get there for some reason we have yet to discover, it definitely seems like a plausible scenario. Awesome. Well, Hamia, thanks so much. This is just like absolutely fascinating. Great overview of all your work. Is there anywhere you'd recommend people go if they want to follow this kind of AI tracking work that you're doing?
Absolutely. So I think that the best way to find our work is in the alignment forum. There is a sequence called Trends in Machine Learning, where like there is an overview of summaries of all our work, which is a great entry point to everything that we're doing and that we're planning to do in the future.
Fantastic. Okay, I will. I'll link to that in the blog post that'll come with the podcast. I'll also link to your Twitter account because I know you do a lot of some interesting like tweeting on this general topic and in topics around this topic. So yeah, everybody definitely check that out. And Jaime, thanks so much for joining me for this. It was a ton of fun.
Thank you for having me, Jeremy. Have a great day.